All right. Well, thank you for being here on a Friday. We're getting closer and closer to the end of the class. We've now finished introducing internal combustion engines, and today we're going to move on to describing how we model internal combustion engines using an air standard Otto cycle. So we talked about internal combustion engines. We sort of defined some terms, and we know that these types of engines are sort of ubiquitous use here in North America. So we're going to start to learn how to do an analysis by making some assumptions. We know that just to get to some kind of an answer where we can sort of solve these kind of problems with pen and paper, we have to make a whole lot of assumptions, in fact, because these are very complicated processes. The cycle is not adiabatic. There's combustion of an air-fuel mixture, so the gas or the working fluid is changing over time, and there's chemical reactions that are happening inside of it. Kinetic energy might be important as pistons are moving up and down inside the engine. It's a transient cycle in that things like pressure and temperature are changing inside the piston cylinder assembly over time. And it's sometimes an open system when either the exhaust or intake valves are open, and sometimes a closed system when both of those valves are closed. So we have to, in order to sort of get the benefit of solving these types of problems using a pen and paper, we have to make some sacrifices. And those sacrifices involve making a series of assumptions. We have to remember that every time we make one of these assumptions, we're kind of stepping further away from kind of the actual universe, right? And moving more towards kind of a cartoon version of the universe, right? And that's okay, provided that we can still get some usable information from the system, right? Or from the model that we're putting together. And oftentimes as engineers, that's kind of our job, right? That's kind of the mantle that we're wearing, is that we're responsible for improving or designing systems even though we don't have perfect information. So when we use an air standard analysis for an Otto cycle or a diesel cycle, we'll make a series of assumptions, including that we'll neglect combustion. We'll assume that heat gets transferred into the system and out of the system, but that there's no chemical reaction, there's no burning of fuel inside of our cylinder. We will assume that all the processes within the cycle can be modeled as a closed system, which means that we use closed system first and second law, and we don't really need to use conservation of mass because the mass is just always inside the system. We'll assume that all the processes are reversible, meaning that they're not generating entropy. We'll also assume that the working fluid is an ideal gas or air, even though this is not true because in real life there's this air-fuel mixture, right? And that's changing over time as we're burning the fuel. And we'll also sometimes make the further assumption that the air has a constant specific heat. Sometimes we call that a cold air standard analysis. Now that's one more analysis to add, or one more assumption to add to the pile here. And, that's another one that takes us further away from sort of the actual answer that's correct, right? But it doesn't mean that it's necessarily, we're not necessarily losing the ability to understand how to make the system better, even though we're making a lot of these simplifying assumptions. But it is important for us to remember that the results that we get are more qualitative than quantitative, meaning that maybe we can understand how changing a certain parameter like compression ratio can change how much power we generate inside of our engine. But the number that we get, let's say that we're producing 100 horsepower using this analysis, it doesn't necessarily mean that that's the right answer, right? So you'd still want to do a numerical analysis and then ultimately build some kind of a prototype and test that so that you understand how your system actually works in real life. So we're going to assume that all the processes here are closed systems. Now, maybe we've forgotten a little bit about closed systems, but this was kind of what we were doing for the first third of this class. And we know that the first law for closed systems looked like this. at least after we've neglected changes in kinetic and potential energy, we get that the change in internal energy is equal to heat in minus work out, right? And we get this little schematic down here that we talked about for the first couple of weeks in this course. Now, how do we find work and heat in an internal combustion engine? Right? So we start with the first law, right? That's almost always the answer in thermodynamics, is use the first law, right? But in this case, particularly when we're talking about the Otto cycle, we'll make the assumptions that every process is a simple process. Now, that doesn't necessarily mean that it's easy to analyze. It means that every process, either work or heat, is dominated, or is the dominating component. So we're going to neglect either Q or W for all the processes inside this Otto cycle. So if we have a passive process, then that means there's no work. So that means we're either adding heat or we're rejecting heat, right? And in that case, we'll find that Q, as we move between state A and state B, is going to be UB minus UA, or U at the end of the process minus U at the beginning of the process. And if the process is adiabatic means, perfectly insulated, so no heat transfer, then we'll try to find the work, and the work is going to be U at the beginning of the process minus U at the end of the process. Right? You don't have to memorize these things because they come right from the first law. So once we sort of apply the first law here, we'll get to the point where we'll need to fix the states. We'll need to find the specific internal energy. And in order to do that, we have to ask ourselves, what's the fluid? And the fluid in these internal combustion engines is an ideal gas. So it's air, and that air is an ideal gas. And that means that it opens up to us the ability to use the ideal gas law. There's a couple different ways that we can use the ideal gas law. We can say that P times the specific volume is equal to RT. Remember, R is the specific gas constant. We take the universal gas constant and divide by the molar mass. But we can also use this equation, P times the volume is equal to MRT. Right? Or if we're bouncing between states, we recognize that because all these systems are closed systems and there's no chemical reaction happening, that means that M is constant and R is constant. So P1 V1 divided by T1 is equal to P2 V2 over T2. Now this is true for volumes as it's written out here, but if I divide all three of these sort of terms by the mass, then what I get is P1 times the specific volume at 1 divided by the temperature at 1 is equal to P2 times the specific volume at 2 divided by T2, and all of that would be equal to the specific gas constant, R. So we can use this ideal gas law more than once in each problem, and we will almost certainly have to do that, right? Because we can look at this for every process. We have the potential to use this version of the ideal gas law where we're bouncing between states, and at every state, we have the potential to use this version of the ideal gas law to fix a particular parameter. So how else can we find the temperature or the specific internal energy? When we have ideal gases, right? And now this is the first cycle that we've looked at where we have ideal gas or air as the working fluid. But when we do this, it's really, really important that we recognize which processes are isentropic, right? So when we have an ideal gas, right? Remember, the what's the fluid question is always a two-part question, right? So if this was water, we would first say, oh, it's water. And then we would say, oh, what's the phase? Is it subcooled liquid, or is it some, mixture of saturated vapor and saturated liquid, or is it a superheated vapor? But if our working fluid is an ideal gas like air, then our question becomes, are we going to use variable specific heat, or are we going to use constant specific heat? So if we use variable specific heat, the change in the specific internal energy that we get from our first law equation is going to remain the change in the specific internal energy. This means we're going to use tables like table A22 for air in the textbook. We're going to use those tables to find the specific internal energies at every state. right? These will be a function of temperature, or as we'll see, reduced volume or reduced pressure. But we'll find these values for specific internal energy on table A22. Right here, because we know the specific heat is changing with temperature, we got to look this stuff up on the table because it's really a nonlinear function. Right? But, one of the ways that we can deal with nonlinear functions is just to pretend that they're linear. And here, if we're assuming that the process is linear here, we would say that delta U is equal to CV, remember that's the specific heat at constant volume, multiplied by the change in temperature. Now, this assumption is pretty good when temperature differences are small, but gets worse as temperature differences get bigger. So when we look this stuff up on a table, it probably takes us a little bit more work, right? But we get a more accurate answer. So it's kind of a trade-off here, and that's kind of the life of the engineer too, is that we'll often have to, pick between, benefits and costs, right? So we have to make these trade-offs, right? So like I was saying though, when the working fluid is an ideal gas, the trick is identifying which of the processes are isentropic, right? Or where is delta S equal to 0. And if you remember what the second law looks like, you're gonna have that Q over T term, right? Or Q dot over T term, right? And when that exists, delta S can never be 0. So in order for a process to be isentropic, you need to say that it's at steady state, right? You need to have it be, it's got to be ideal, right? So that entropy generation term goes to 0, and it's got to be adiabatic. So we got to be able to identify which of these processes are isentropic because there's some special equations that we can use when the process is isentropic. Now these equations, they look different if it's variable specific heat or constant specific heat. So if you look on table A22, it's going to have a couple of columns, right, that show you PR and VR. Now these are not the specific volumes and the pressures, right? Instead, they're the reduced specific volumes and the reduced pressures. So what happens is if you have an ideal gas and the process is isentropic, then you can say this ratio of reduced specific volumes is equal to the ratio of the specific volumes, which is also equal to the ratio of the actual volumes if you're talking about a closed system, right? And this is good because if you remember, for these internal combustion engines, we often talk about a volume ratio, right? We call that the compression ratio, which is the volume at bottom dead center divided by the volume at top dead center, and that should be always greater than 1. Now, you'll also want to identify isentropic processes if you're talking about constant specific heats, but in these cases, we're going to look for an equation that has K in the exponent. Remember, K is the specific heat ratio. It should also always be greater than 1, and it's going to be Cp divided by Cv. Now, because when we talk about these internal combustion engines and their closed systems, we'll often know volume ratios. So for these internal combustion engines, the expression with K in the exponent that we're going to use here relates this ratio of temperatures to a ratio of specific volumes, or volumes, because again, the mass is constant, to the power of K minus 1. Now remember, in this case, these are not delta T divided by delta T, it's T over T, so we have to use absolute temperatures, right? So we need to use Kelvin or Rankine here. We can't use Celsius or Fahrenheit. So now we're going to get away from talking sort of generally about these internal combustion engines and look specifically at how we model an engine as an Otto cycle. So the air standard Otto cycle consists of 4 internally reversible processes. Remember, we say that all of these processes are ideal, right? That means they're reversible or that they're not generating entropy. But just because you're ideal or you're not generating entropy doesn't mean that you're isentropic, because sometimes you're adding heat and that Q over T term is going to stick around. So the first process is our compression, right? So here we're going to move from state 1 to state 2. And on a PV diagram, what happens is our volume gets smaller and our pressure gets bigger, right? We're compressing the fluid. This is the compression stroke, right? Now on our TS diagram, because here we're putting work into the fluid. So we assume this is adiabatic. So this is one of those isentropic processes we were talking about. One of the keys to be able to solve this system is recognizing which processes are isentropic. So it helps to be able to draw a TS diagram here. Next, we'll look at process 2 to 3. This is constant volume heat addition. So this is what sort of is, makes an Otto cycle an Otto cycle. Remember we talked a little bit last class about the difference between an Otto cycle and a diesel cycle? The Otto cycle, we assume that heat addition happens at constant volume. We'll talk about diesel cycles next class, where we assume that heat addition happens at constant pressure. So here the Otto cycle, heat's added at constant volume. That means as I move from state 2 to 3 on my PV diagram, I have a vertical line. Now, you may remember this from the first third of the course, but this is a beautiful thing because you know that work is the integral of PdV. And if delta V is 0, work is 0, right? And that makes sense because here we're saying this is a passive process. So only heat transfer is happening here because it's a simple process, right? Where simple means only one of the two things, heat and work, sticks around. Next, we're going to have the isentropic expansion, right? This is, the whole reason that we're running the internal combustion engine, right? This is sort of equivalent to now we're burning the fuel in the cylinder, the gas is expanding, and it's pushing that cylinder down. So as the cylinder gets pushed down, we increase the volume and we drop the pressure, right? This is doing work on the piston. This is, again, an adiabatic process, or at least that's the assumption that we'll make. So because it's adiabatic and it's ideal and we have a process, well, I guess if we were doing this in a first law state, we would say this was a steady state process, right? And we would get that delta S is equal to 0, right? Or that this is an isentropic process. So the isentropic processes, the keys to this process or this cycle are going to be knowing that the compression and the expansion, the places where we're doing work, those are the isentropic processes, right? So that's where we can use those special equations. Next, we have to reject heat. So as we move from state 4 to state 1, this is constant volume heat rejection. So on our PV diagram, we have a vertical line, right? And we're moving down here. And this is where we're rejecting heat, right? This is the sort of air standard analysis equivalent of opening up that intake valve and moving the piston down. Right? So remember, in the Otto cycle, there's only two volumes, right? There's the big volume, which is volume 4, but it's also volume 1. And there's the small volume, which is volume 2 and volume 3, right? There's only two volumes in this problem, right? Even though there's 4 states. Our compression ratio is going to be bigger than 1. So we take the big volume divided by the small volume, right? So we can write that as V1 over V2 or V4 over V3 or any kind of permutation of the big volume divided by the small volume. Now, here's kind of a cartoon sketch of what an Otto cycle kind of looks like, right? So this, I hope, is helpful for remembering what these different processes are, but remember, this is a model of how an internal combustion engine works, and this is not actually how an internal combustion engine works, right? So this is kind of a cartoon that we're trying to use so that we can understand approximately how we can make our internal combustion engine work better, right? So this first process is our compression process, right? So what happens is it's like the piston here is moving up, right? That compresses our gas, it increases our pressure, and it increases our temperature. Now our second process is this heat addition, right? So this is kind of like, again, not how it works in a real engine, but it's almost like the piston dwells here for a little bit. It just pauses, and we add some heat, right? And remember, this is how we're modeling the combustion of the fuel, right? As we're saying, well, we're just going to say it's a constant volume heat addition process. So we're going to say the volume stays constant. We're going to add some heat here. Then we get this power stroke, right, or the expansion, and now our piston's moving down because that gas is expanding, and as it expands, it pushes the piston down, and we're getting work out, right? This is our third process, and now again, we have a constant volume heat transfer, right? But now heat is leaving the system, right? So here in our fourth process, we get heat rejection at constant volume. So this is kind of the storyboard of what an Otto cycle would look like if it was real. But remember, it's not exactly real, right? It's just the way that we're going to model the process so that we can sort of get an answer that helps us understand how to make the engine work better, or get a ballpark estimate of how much power we get, or maybe what the thermal efficiency is. So if I have to draw a PV or a TS diagram, right, and this is certainly something that we can ask you on the exam, right? You're going to have to draw PV and TS diagrams on the exam, or in a multiple choice question, you're going to have to be able to identify which PV diagram goes with which cycle, right? So here, our first process, as we move from state 1 to state 2, this is compression, so we're putting work in to the cycle, right, into the working fluid. Our second process is constant volume heat addition, right? So here, remember, pressure was constant, right? So this is a vertical line, no area under a vertical line, so there's no work here. Our third process is our power stroke. Here we're getting work out because the fluid is expanding and pushing that piston down. And then we're going to reject some heat as we sort of move from state 4 to state 1, right? Remember, all of these cycles, we want to get back to the beginning, right? So that we can keep running and running and running. The other thing, right, because here the working fluid is air, so we need to be able to identify the processes where they're isentropic, and those are going to be the processes where we're only doing work. They're also the processes with vertical lines on a TS diagram, whether it's going up, like from state 1 to state 2, or down from state 3 to state 4. So how do we do the analysis, right? So we're assuming all these processes are constant mass, right? So they're closed systems. So common assumptions that we'll make, we'll say that it's at steady state, although that doesn't actually come into play here, that there's a closed system, right? Because it's a closed system, we get rid of any of the terms here that would be related to m dot, right? Or the mass flow rate terms. There is no mass flow rate here. All the mass stays inside the piston. We're going to say that the change in kinetic energy can be neglected. The change in potential energy can be neglected. We're going to then say that each process in this case is either adiabatic or passive, right? And here, really, I could find the work for these processes that I'm saying are passive, but they're vertical lines, right? And work is the integral of PdV, and if delta V is 0, then the work is also 0, right? So here, all the processes are either adiabatic or passive, and the ones that are isentropic, which is kind of the key to solving these things, they're the ones where they're adiabatic, where I'm only solving for work. We're also here assuming that all the processes are reversible, or that they're ideal processes that aren't generating any entropy. So when we do that, we're going to get expressions for each one of our processes. Our power stroke, we're going to find that the work is going to be mass times U3 minus U4, as long as our state numbering is the same as it was in the diagram. We're going to assume, right, because this is work out, right? Work in is negative, so that means work out is positive. Heat rejection, right? So we're losing heat, so this is a negative number. This is going to be m times u at the end of the process minus u at the beginning of the process. Our compression, right? This is us putting work in, so this is m, just like the last work term, this is m times u at the beginning of the process minus u at the end of the process. But here, right, because hip to win says that work in is negative, so this is a negative number. And then heat addition, right, this is kind of the equivalent of burning the fuel. This is, again, going to be m times u at the end of the process minus u at the beginning of the process. And here we're adding heat, so we expect this number to be positive. So you don't have to memorize any of these equations. They come from the first law, right? So if you know the assumptions that you're going to make for each process, it's not that hard to derive these equations for each one of these processes. But after you do it enough times, you can just tell me what these equations are on an exam. But when you do, make sure you tell me what assumptions you're making. So as always, my advice is start with the first law, and then as you're crossing off terms, you're telling me what the assumptions you're making are, right? And that's really important as an engineer to understand the assumptions that are going into your model so that you know if you get results that you want to get more accurate, you look at your assumptions and you start to think, which of these assumptions should I relax, right? When we look at this, the next thing we'll say is, what's the fluid, right? Because now we've got all these equations that have delta U's in them, and I got to be able to fix my states, right? And if I'm using variable specific heat, this means looking stuff up on A22 if it's air, right? And if it's constant specific heat, I'm never going to find the individual specific internal energies, but I'm going to say that the change in the specific internal energies, which is what the first law tells me about, is going to be CV times delta T. My thermal efficiency is going to look like this, right? Because now I have work out, that's my compression, or that's my expansion, right? My power stroke. My work in is my compression stroke. I'm adding these things together and trusting the first law to give me the right signs, and I divide by my heat in, right? Because the thermal efficiency is going to be the energy benefit, which is net work, divided by the energy cost, which is heat in. Right here, if I sort of manipulate the terms a little bit, I can get something that's U3 minus U2, and then minus U4 minus U1, right? So here I can get 1 minus this term over here, right? I can also express my thermal efficiency. I can use the works, but if I don't know the mass, that's okay, because all of these terms are multiplied by mass, but the mass is the same in each one of these processes, so it can drop out, and I can just deal with the specific internal energies, right? And if I do this, I get this expression, right? And this can also be written, remember, because this is we're assuming everything here is reversible, so the work out minus the work in, right, is the same as the Q in plus Q out. So net heat is equal to net work, right? And if I do this, I get the same answer, which is good because, the answer you get should be independent of the method that you use, right? So here, if I think about this as net heat over heat in, and if I think about it as net work over heat in, I get the same answer, right? And that's always a good thing. So now I want to be able to fix these values for you, right? And one way is that I can use the ideal gas law, right, in either of these two forms as I'm moving between states, or I can say that P1 V1 is equal to MRT1, right? Or if I want to use specific volumes, P1 times little v1 is equal to RT1, right? I can do that at any state, and I can bounce between states using these expressions that are here, right? And now I got to be able to identify the isentropic processes, because Dr. Scherzer told me this is the key to sort of solving any of these cycles that use ideal gas as the working fluid. So the processes that are isentropic are the ones where we're either putting work in or getting work out, and they're adiabatic, right? So this is our compression stroke and our power stroke here. So in these two processes, I can use either constant specific heat. I can find an expression with K in the exponent. For these internal combustion engines, usually I'll use this expression here that's spotlighted because I'll know the volume ratios, right? Because I know that compression ratio, which is a ratio of volumes. If I'm using variable specific heat, then I'll use here probably that the ratio of the reduced volumes is equal to the ratio of the volumes, or the ratio of the specific volumes, right? And I remember that my big volume divided by my little volume is equal to the compression ratio here. So I get PR and VR, and because this is a internal combustion engine with closed processes, I'll probably be looking for these reduced specific volumes, and I'll get those on table A22 or A22E if I have an imperial problem. So for my air standard Otto cycle, it's got these four processes, right? I can draw them out on a TS diagram or a PV diagram, and the cool thing is the area inside my TS diagram is the net heat, and the area inside my PV diagram is the net work. So this is kind of neat because I can, this is one of the advantages of this model. Even though this is a bit of a cartoon of how an internal combustion engine works, we can see pretty easily how changing some parameters can change how the engine's going to perform, right? So I know that the net heat is equal to the net work. So the area inside both of these curves should be equal. So why does this matter, right? So let's say, compression ratio is something that, if you read about, some new engine that gets put out, right? Or you read about a car that you want to buy, in that owner's manual, it'll probably talk about the compression ratio of the engine, right? This compression ratio is the big volume divided by the little volume, right? So on this TS diagram, if I have an engine with a lower compression ratio, then I'm going from state 1 to state 2 to state 3 to state 4. If I have a larger compression ratio, then I go from 1 to 2 prime to 3 prime down to 4, right? Now, when you look at this, you can tell me right away which of these two engines is going to deliver more net work, right? Because the net work per cycle is given by the area inside the cycle on the TS diagram, right? Because here you see as R goes up, the area on the TS diagram goes up, which means the area on the PV diagram would also go up. That means that the net heat goes up, but it also means because the net heat is equal to the net work in this case, that the net work goes up, right? So if I was running at the same speed and they were both 4-stroke engines, that would also mean that the net power goes up, right? So here, even though this model, it makes a lot of assumptions, we can see how performance changes with changes in compression ratio, right? So increasing the compression ratio increases the net work, right? But there's a cost to this too, right? So maybe maybe if you buy a Bugatti or something, it's got like some enormous amount of power that it can produce, right? But the cost is that we're also increasing the heat, right? Which means that we're probably increasing the heat that we're rejecting, right? Which means we're going to go through more gas, right? So, it's hard, unless you sort of come up with some new engine type, it's hard to increase both net work and fuel economy, right? So usually in engineering, we're talking about trade-offs, right? So you can make an engine that develops more power, but the cost is probably that your fuel economy is going to go down, right? So now that we've talked a little bit about these Otto cycles, I want to go through an example, right? And I'll go through it in constant specific heat and variable specific heat too. But just before that, I'm going to pause for a couple seconds here to see if anybody has any questions about what we've talked about to this point. Okay, as always, feel free to interrupt me either by, writing something in the chat, by putting your hand up icon, or just unmuting yourself and asking a question, okay? So we're going to go through a problem here. So this is an Otto cycle, right? I'm nice in this particular example that I drew the PV diagram and the TV diagram. So you can see, or a TS diagram. On this TS diagram, you can see pretty clearly which are the isentropic processes. This is an imperial problem. So we have CV, CP, and R all given, but in imperial units. We're told the temperature at state 1, the pressure at state 1, the compression ratio, right? That's going to be V1 divided by V2, our big volume divided by our little volume. We're told that's 10. We're told the pressure at state 3, and we're also told the volume at state 4. Finally, we're told that this is a 4-cylinder, 4-stroke engine with a RPM, or rotational speed, of 2,000 rotations per minute. So, what do we do? How do we solve this problem? Right? So, again, my first advice, right, if this is an exam and you don't know what to do, try to get the symbolic solutions for all the parts of the problem. Right? Because if you do that, you're demonstrating that you understand how to use the first law for different cases, and you'll get, a significant amount of the grades in a probably low amount of time, right? So here we're going to go through the same assumptions that we went through when we were deriving these equations earlier in the class. We're going to find that if we're trying to find work, it's going to be mass times U at the beginning of the process minus U at the end of the process. If we're trying to find heat, that's going to be mass times U at the end of the process minus U at the beginning of the process. Now, Dr. Scherzer told me that the key to these processes, or these cycles, is to identify the isentropic processes, so I've circled those in red here. These are the ones that are adiabatic when we're trying to find work, right? So it's our power stroke and our compression stroke. I've also written down which one of these terms I expect to be positive and which ones I expect to be negative. After I do this, I'm going to show you how to solve these states using both variable specific heat and constant specific heat. Remembering that with constant specific heat, I'm never going to find the individual specific internal energies. Instead, I'm going to find the change in U, which is all the first law asks of me, and that's going to be CV multiplied by delta T. So my symbolic solution, it's asking for net power in this particular problem. So that's going to be, first I got to get my net work, right, which is going to be the sum of my compression stroke and my power stroke, right? I remember the compression stroke is going to be negative, right? So I want to check my units here just to make sure it makes sense. It's an imperial problem, so, things can always get weird in imperial problems. So I know my mass is in pounds mass. U or delta U will be in BTU per pounds mass, right? So this gives me an answer in BTU. But if I look at an engine in imperial units, usually if it talks about power, it'll talk about horsepower, right? So we got to think about when we're doing power, how do we change from BTU, which is a unit of energy, into power, which is horsepower in this case. So to find the power here, or W dot net, I take the net work, which is in BTU. Now I got to remember how many rotations per minute do I have, right? That's the rotational speed. I was told that. But then I got to remember, is it a two-stroke engine or a four-stroke engine? Every revolution, right, or every rotation of my drive shaft is going to give me 2 strokes. So if it's a 4-stroke engine, like we're talking about here, I need 2 rotations to perform 1 cycle. So this net work is the work per cycle, right? So this is BTU per cycle. So if I do this calculation, W times N multiplied by 1 cycle divided by 2 rotations, that will give me how many BTU per minute my engine produces, right? But we probably don't want BTU per minute. We probably want power in terms of horsepower here. So I look on the equation sheet that you'll get for the class, and that tells you that 1 horsepower is equal to 42.4 BTU per minute. So we can use that conversion here to get an equation for the power that's developed by my engine here. So now I want to take stock of the things that I know and the things that I don't know. So I don't know net work, so I can't jump right into this power calculation. I got to use the first equation that I have here. I don't know the mass. I don't know U1, U2, or the difference between U1 and U2. I also don't know U3 or U4 or the difference between U3 and U4. I don't know the net work, right? I said that already. I do know the rotational speed. So there is something in here that I know. I know N, and I also know this conversion factor, right? But I got 2 equations, and I got a whole bunch of unknowns, right? And that's not great because it means I can't get a numerical answer yet. So in order to do this, I need to solve for the mass, and I need to get values for the specific internal energies, or at least for the change in specific internal energy between state 1 and state 2, and state 3 and state 4. So the first thing that I want to do is I want to find the mass, right? Because eventually I'm going to have to pick, is it standard, is it constant specific heat or variable specific heat? But I don't have to do that yet because I can find the mass with the ideal gas law. So I'm not forced to pick constant or variable specific heat yet, right? So if I can find a state where I know a bunch of stuff, then I can use the ideal gas law. PV is equal to mRT. This equation has mass in it, which is good because I'm trying to find the mass. So here I can isolate for mass. It's PV divided by RT. So if there's some state where I know PV and T, R is constant for the whole process, then I'll be able to find the mass. Right? So here, state 1 is the state that I know the most about, right? This is, again, a benefit of having a state table because you can just look at it and see where do you know the most information, right? So I know a lot about state 1, but I don't have the volume at state 1. But I remember that there's only 2 volumes in the problem, and the volume at 4 is equal to the volume at 1, and on my state table, I know the volume at 4. So I do know the volume at 1. And if I wanted to go real quick and find the volume at 2 and 3, that's just going to be the volume at 4 divided by 10, because my compression ratio here is 10. Right? So if I look here at state 1, I know P1. Now I know V1 because it's the same as V4. And I know T1. I got to remember, because this is not a delta T, I got to use Rankine. I think the problem here is nice to me and gave me the temperature in Rankine, but if it was in Fahrenheit, I'd have to convert, right? And I do have to deal with the fact that the volume was in inches squared, so I got to change that, right? And this equation will, there's another unit conversion that I have to do here to convert between foot-pounds force and BTU. So you always got to track your units, and you got to be double careful when you're doing imperial problems. But if I do all this, I put it all into my calculator, I track my units, and I find that the mass is 0.0015 pounds mass. So that's good, right? I have the mass. There's still a lot of stuff I don't know in this problem, but the stuff I don't know is really all specific internal energies. If I can find the specific internal energies at 1, 2, 3, and 4, or the change between 1 and 2 and the change between 3 and 4, then I put that in here. That's going to tell me what the net work is. I'll put the net work in here and I'll have the power. So now I'm at the point where I got to choose between constant specific heat and variable specific heat. But lucky for you, we're going to do it both ways, right? So you can see how to do this both ways, right? So if you were doing a problem on an exam, I would encourage you, I'd tell you to do this one way or the other, right? You'll get more points if you do it the way that I ask you to do it. But if you can't remember how to do it that way, but you do remember how to do it the other way, like, so if I tell you to use variable specific heat, you're like, I don't remember how to do that. Doing it with constant specific heat is certainly better than not doing it, right? So first we're going to assume that this is an air standard analysis with variable specific heat. So now what do? I look at my state table. I'm going to start on my state table almost always with the state that I know the most about. Now, if it's variable specific heat, it means I got to use table A22 to look stuff up, right? Now, the cool thing about table A22 is once I know one thing on the row in A22, I know everything, right? So here, I know the temperature. Temperature is one of the things on A22. So for state 1, I can interpolate to find U. And the other thing I'm going to want to pick off the table here is VR. Because remember, the key to these cycles where you have ideal gas as the working fluid, the key is to identify these isentropic processes, right? Because then the ratio of VRs is going to be equal to the ratio of volumes. So it's going to be important to pick off VR here too. Typically, when we're using table A22 for internal combustion engines, in the state, we're either going to know the temperature, which will let us interpolate, or we're going to know VR, and then we can interpolate to find U and T. So I'm done here with state 1. Now I got to move between state 1 and state 2. Right? So this is an ideal gas. I can always use the ideal gas law as I move between state 1 and state 2. But remember, I'm telling you that it's really important to know which one of these processes are isentropic. So as we move from state 1 to state 2, this is a compression stroke, right? So here it's adiabatic and we're trying to find work. So here, this is one of those processes that's isentropic. Because it's isentropic, I can use this expression that the ratio of the reduced volumes is equal to the ratio of the volumes. I know that V2 over V1 is 1 divided by the compression ratio, or 1 over 10. Here I picked off VR1 from the table, right, when I was interpolating at that temperature. So that means I can find VR2. Now, once I know VR2, I can interpolate back. This is just like knowing the temperature, because once I know one thing here, I can interpolate back. So now I'm trying to color code where you get each piece of information, right? So the red stuff here, this was something that I got from this isentropic expression. Now I'm going to interpolate on table A22. I'll find the temperature and I'll find the specific internal energy, right? So here, right, we're compressing the fluid. So it does make sense that the specific internal energy went up, right? We're putting work in to increase the specific internal energy, and that's what happened. You'll notice here we don't know the pressure. I can't get the pressure off table A22 because A22 doesn't tell me anything about pressures, even though it might tell me something about PR, right, or the reduced pressure. So here, I have to use the ideal gas law to find the pressure at 2. Now, maybe you would skip this part. And if you did, I'll show you what would happen, right? But I've done these problems before, and I know that I need to know the pressure at state 2. So if you skip this, you'd find out later that you need to go back and find it. So I'm just going to find it now, right? So here's the ideal gas law. P1V1 over T1 is equal to P2V2 over T2. So I can isolate for P2. It's going to be P2 is equal to P1 times the volume ratio times the temperature ratio. So in here, my pressure goes up. This is no surprise in the compression stroke that we increase the pressure, right? That's kind of why we're doing this. So now we're going to go between state 2 and state 3. What happens between state 2 and state 3? We add heat. If we add heat, that means it's not an isentropic process. It means I can't use the isentropic relationships. That means the only thing I can do is use the ideal gas law, right? So here, as I move between state 2 and state 3, I can use the ideal gas law. The thing I want to find here is the temperature, because if I know the temperature, then I can go to table A22 and I can find the specific internal energy and I can find VR. Here, P3V3 over T3 is equal to P2V2 over T2, right? That's the ideal gas law. I'm trying to find T3. So this is going to be T2 times a volume ratio times a pressure ratio. Now here, if I didn't use the ideal gas law to find this pressure, then I would get to this expression and I wouldn't know T3 or P2. So then I'd have to go back and pick off P2. But since I know that already, now I know that the temperature goes up. This is no surprise because we're adding heat, right? So the temperature goes up. Now I know that the temperature here is 3820 Rankine, right? So now I can go to table A22 and I can get a specific internal energy and I can get a value for VR, right? Notice here that these VRs are not the same, right? Even though the volume didn't change, VR changed because this is not an isentropic process. So we can't use that isentropic relationship here. So now I'm done with state 3 and I need to find state 4. Right? As I move between state 3 and state 4, remember, this is the whole reason we're running this internal combustion engine, so that we can get work out, right? This is our power stroke. We're getting work here. It's adiabatic. That means that it's isentropic too. So I can use my isentropic relationship to find VR4, right? So here I know VR4 divided by VR3 is equal to V4 over V3. V4 over V3 is equal to the compression ratio. That's 10. So V4 is going to be 10 times, or VR4 is going to be 10 times VR3, or 5.22. Now, I go to table A22, and I interpolate. I can find the specific internal energy, and I can go back and find the temperature. So now I know all those specific internal energies. Because I know all the specific internal energies and I found the mass, I can find the net work. And the net work was the only thing I didn't know in my net power calculation. So here, I go in, I check my units, right? I put some stuff into my calculator and I find that the net work is 0.4472 BTU. Now, I gotta go and I gotta multiply by N over 2, that's my RPM. I'm dividing by 2 here because it's a 4-stroke engine. Here, now, I'm also got to use this conversion to get to horsepower, right? And in this case, I get 10.5 horsepower in my engine after I put all that stuff into my calculation. So now I found the net power. And the problem would be over if I was doing a variable specific heat analysis. But remember, this was a bit of a choose your own adventure when we got to the symbolic solution. I got to pick, am I going to do a variable specific heat problem or a constant specific heat problem, right? So I chose variable specific heat before, but I can also do this problem if I assume specific heats are constant, and that opens up to me equations like delta U is equal to CV times delta T, right? So I can do this for U1 minus U2 and for U3 minus U4. When I do this, I'm never going to find the individual specific internal energies. But that's okay, because my expression talks about the changes in the specific internal energies, right? So how would I go about doing this? Again, I'm going to start at state 1 and march my way through, right? The beauty of the cold air standard, the benefit here is that I don't have to do any kind of interpolation. The cost is that I'm less accurate, right? Because I'm sort of taking one more step away from what reality looks like, right? So as I go from state 1 to state 2, remember this is an isentropic process. An isentropic process between state 1 and state 2 in a cold air standard analysis, right? Here we're looking for a temperature ratio as a function of a volume ratio in an expression that has K in the exponent, right? So here I can isolate this for the temperatures, right? So I can find T2, right? And again, I got to make sure that T1 is in Rankine. But after I do this, I see that T2 is 1,336.6. So up to this point, it's kind of, even though I'm using a different expression, kind of the same order that I did things in for the variable specific heat problem, right? And you'll notice that. But the good thing is now I don't have to interpolate. I don't need to interpolate anywhere because I don't have to find U and I don't have to find VR. I just get the temperature. The temperature is actually the unknown in my equation for the first law. I'm still going to have to use the ideal gas law between state 1 and state 2, and I'm going to get an increase in pressure, which is not surprising in the compression stroke, right? Its job is to increase the pressure of the air. That's what we've done. Now I'm going to move between state 2 and state 3, right? This is my heat addition process. This is not an isentropic process, so the only equation that I can use here is the ideal gas law equation. Here, right, for the ideal gas law, I can find the pressure, P3, and again, if I hadn't already found P2, then I would have two unknowns here, right? I wouldn't know the temperature at state 3, and I wouldn't know the pressure at state 2, so I'd have to go back and find it. But since I already did, I find that the temperature here at state 3 is 3,820.9 degrees Rankine. So now I use the ideal gas law to get T3. So now I'm done with state 3 because the only thing that I want to know is the temperature at state 3. Now I look between state 3 and state 4. I notice this is an isentropic process. Because this is an isentropic process, I can use this expression for isentropic processes, right? I get that T4 over T3 is equal to this volume ratio multiplied by K minus, or to the power of K minus 1. I know V3 over V4, these are specific volumes, but it's the same, right, as the ratio of the volumes, right? So here I can use my compression ratio to find this answer, and I get that my temperature at state 4 is 1,486.5. I could find the pressure at state 4 if I wanted to, but it's not in my expression, right? So unless a problem specifically asked, hey, what's the pressure at state 4? I don't care, because here I'm trying to find the net power, so I need the net work, and the net work is a function of the temperatures, but not the pressures. So I'm not going to find the pressure at state 4. But I could use the ideal gas law if I wanted to. Right, so here now I have this expression for net work, m times CV times T1 minus T2 plus T3 minus T4. I know all these temperatures, right? I know the mass, I know CV. So here, when I go through, I get that the net work is 0.389 BTU. I put this into my expression for power, just like I did with a variable specific heat problem. Now, again, we've converged, right? We're doing the same thing we did in the variable specific heat problem. I got to multiply by n over 2, right? Because I need 2 revolutions per cycle. And then I convert from BTU per minute to horsepower. And now I get an answer of 9.2 horsepower, right? So it makes a difference in my final answer which method that I use, right? I know that if I've assumed that this is a constant specific heat problem, that my answer is less accurate, right? But it's still valid in kind of getting me into the ballpark, right? Or seeing what happens if I change my compression ratio. Is my power going to go up or down, right? So remember, these are models. They're not reality, right? And that's kind of what we do as engineers, right? So hopefully that gives you an idea of how to do these Otto cycle problems. So again, I'll post this online, but you can also look at the pre-recorded lecture, which is really just the same material, but taught on a different day. So maybe the wording's all a little bit different. But that's all that I had for you today. If you have any questions, I'm happy to entertain them now. Otherwise, I will see you on Monday. All right, everyone, have a good weekend.